hot Jupiters, one roasted and one with its hotspot in the wrong place. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Coming up, I'm joined by Tiffany Kataria, a research scientist at NASA's Jet Propulsion Laboratory, and Lisa Dang, assistant professor at the University of Waterloo, to talk about two hot Jupiter headlines that are straight from the 248th American Astronomical Society meeting. HD 80606b is an eccentric giant that spends most of its year cold and quiet, then gets slammed with flash heating for just a day or two as it swings close to its star. Another exoplanet, called Corot 2b, is a puffed-up world whose hottest point shows up in an unexpected location. And after that, we'll check in with our chief scientist, Bruce Betts, for What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we get into our main discussion for today, I want you all to know that the Planetary Society is hiring. We're looking for a Salesforce admin/analyst to join our team here in Pasadena. It's a full-time role focused on the technical side of our Salesforce CRM platform. That's the system that powers how we manage membership, process donations, and stay connected with all of you, our members and supporters around the world. If you've got a Salesforce administrator certification, at least 3 years of hand-on development experience, and ideally some familiarity with the Nonprofit Success Pack, we'd love to hear from you. You can find the full job listing and details at planetary.org/careers. The first round of application review is going to begin on August 3rd, so you don't want to wait too long. And now back to our hot Jupiter stories. In June, the American Astronomical Society held its 248th meeting right here in Pasadena. It's one of the biggest gatherings in astronomy. Thousands of scientists, students, and educators come together to share their new results. I was there, and I sat in on a press conference called Fire and Ice in Planetary Systems Near and Far, where these two hot Jupiter stories were presented back to back. The first one, on a planet called HD 80606b, was presented by Dr. Tiffany Kataria. She's a research scientist at NASA's Jet Propulsion Laboratory who focuses on atmospheric dynamics and chemistry. HD 80606b is about 217 light-years away in the constellation of Ursa Major. It's a giant planet that's roughly 4 times the mass of Jupiter, and it orbits a sun-like star every 111 days. But what makes this world extraordinary is its eccentricity. It's one of the most extreme orbits of any known exoplanet. At its farthest, it's about as far from its star as Venus is from our sun. But at its closest, it's 10 times closer than Mercury. Earlier observations with the Spitzer Space Telescope gave us our first look at this world's atmosphere. But Tiffany's team has now captured new data using the MIRI instrument on the James Webb Space Telescope. MIRI looks in the mid-infrared, and it's a data set that was years in the making, as you'll hear in this conversation. There's also a separate set of JWST observations using the NIRSpec instrument from another team. That's in the near infrared. And combining these two datasets promises an even richer picture of what's going on with this world. And you may have actually seen this exoplanet before without knowing it. HD 80606b is the roasted planet from NASA's Galaxy of Horrors poster series, and it honestly earns that name. I walked out with one of those posters myself, and now I'm just looking for a place to frame it in my apartment. Our second story today is on Corot 2b, which was presented by Dr. Aurora Caselli. Aurora is currently on maternity leave, so I want to send a huge congratulations to her and her family. Dr. Lisa Dang is going to be joining us in her place. Both Lisa and Aurora were co-authors on a paper called Unraveling the Mystery of the Peculiar and Young Hot Jupiter Corot 2b, which was published in the Astronomical Journal. Lisa is an assistant professor at the University of Waterloo who studies hot Jupiter atmospheres and lava planets. Corot 2b was discovered back in 2007 by the French-led Corot spacecraft and sits about 700 light-years away in the constellation of Aquila. It orbits a young, active sun-like star, and completes a full orbit in just 1.7 days. It's about 3.3 times Jupiter's mass, but 1.4 times Jupiter's radius, so Corot 2b is noticeably inflated. LISA first mapped this planet's thermal emissions using the Spitzer Space Telescope, and the paper that Aurora presented uses ground-based high-resolution spectroscopy from the Gemini South Telescope to dig further into its atmosphere. Most hot Jupiters on orbits that tight are expected to be tidally locked, but Corot 2b's hotspot shows up in a completely unexpected place, which may mean that this young world hasn't fully tidally locked to its star yet. These two planets are striking examples of just how different hot Jupiters can be from one another. Hey, Lisa and Tiffany, thanks for joining me.
Hey, happy to be here.
Hey, thanks for having us.
So for anyone who hasn't been following exoplanet science closely, and I love exoplanets, I began my start in astrophysics doing exoplanet detection, but I wanted to ask, just for people who are unfamiliar, what exactly is a hot Jupiter?
So a hot Jupiter is a pretty literal name, actually. So it's a Jupiter-sized exoplanet, Jovian-sized exoplanet that orbits very close to its host star. So its hot Jupiters are typically 10 times closer than Mercury orbits our own sun. And so that's why they achieve such high temperatures and why we call them hot.
They're basically like a hot ball of gas, and some of them actually get so hot that it can reach a temperature of like 4,000 Kelvin or 4,000 Celsius at this point. The difference is minor. And so some of them kind of like behave like a star sometimes, or their atmosphere is very similar to some of the coolest stars we have in the galaxy.
Well, these kinds of worlds are a lot more easy to detect than other exoplanets, largely due to observation bias, right? They're close in toward their stars. They're pretty big. But my understanding is that when we first found these, it was actually kind of shocking to us and kind of led to the concept of planetary migration. So is it genuinely hard to form a world of this size that close to the star? And why was that so surprising for people?
Yeah, so I think, in the mid-90s when these planets were first discovered, and actually the first hot Jupiters weren't discovered via transit, they were actually discovered via another exoplanet detection technique called radial velocity, where you're essentially measuring the gravitational tug between your planet and your star. And so the first of those, the first planets that were orbiting sun-like stars were these hot Jupiters that were discovered. And so it was definitely surprising. I think planetary migration in general has been a long-standing field, for our own solar system. We're trying to understand, how the inner terrestrial planets formed and the gas giants and the asteroid belt in between. There wasn't any, previous theories that we should expect to see Jupiter-sized planets super close into their stars. It definitely forced, I think, the field of orbital dynamics and migration, to sort of expand their thinking as to, how a planet like that might exist, and not only exist, but be stable over the lifetimes that would take for us to find them.
What might cause a world of that size to migrate in toward its star?
So that's a big question. I think even though hot Jupiters are thought to have formed further out, like our own Jupiter was, and then later migrated in, it's not the only way that you can form a hot Jupiter. So when 51 Pegasus b, the first hot Jupiter and exoplanet was discovered, it really sparked a revolution in our understanding of planetary migration formation. And so there are some theories that allow planets to form very close in and kind of like stay there. But the majority of the planet that we think went through this process of migration where they formed further out and it created this large envelope of gas before they migrated in. There's a couple of things that can make them migrate in. One of the leading hypotheses is called tidal dissipation. So basically they first start off at a very large distance, and there's something that basically introduced or keep them on an eccentric orbit. So they basically are orbiting on this very elliptical orbit. Most of the moment on the orbit, they're very far away, but occasionally they get very close. And then later on, planets kind of want to find this stable orbit where they become circular. And so they kind of slowly become less and less oval of an orbit, and they can kind of get close in.
That's a really interesting situation to think about, especially since we're about to talk about this roasted planet, HD 80606b. I always feel like it's kind of like reading off a license plate, right?
Yeah.
I wonder if that means that world might be in some way in this earlier phase of migration where it's on this really wild orbit and might eventually circularize.
I mean, given the age of the system, it probably would have circularized by now. So there is a bit larger question about this system, HD 80606b, and how it's able to maintain its high eccentricity or ellipticity. It is, in fact, one of the most eccentric exoplanets that has ever been discovered. And so how, over the lifetime of that system, does it maintain this, this oval shape? I think that is part of what is so exciting about trying to observe and characterize the system and its atmosphere.
Before we get into these actual exoplanets, I wanted to ask you guys about your journey a little bit, because neither of you actually studies planets that resemble anything like what's in our own solar system. So what drew you both personally to these kind of extreme alien environments rather than Earth-like worlds?
I think when I first started looking at exoplanets, we were kind of in this era where we were data deprived. And so we didn't have that many telescopes that could observe a planet outside of the solar system and characterize them in greater details. And so some of the few telescopes that could do this was the Spitzer Space Telescope, which observes in the infrared and therefore is most sensitive to planets that are very, very hot. And so Jupiter just turned out to be some of the best target because not only they're very hot and so they glow in the infrared, but they're also very close in. So we know that there are multiple transits that are happening every couple other days, which made them very amenable for observing and kind of like refining the kind of like techniques that we now use widely to characterize any kind of exoplanets that are more difficult than these hot Jupiters. But they were kind of low-hanging fruits, but I don't want to say that we're only studying them because they are low-hanging fruits. They have a bunch of physics that we don't necessarily have in our own solar system. So that's how I started my journey in exoplanets and studying hot Jupiters. How about you, Tiffany?
So I guess on my end, my background, my PhD is in fact in planetary sciences. And so, as someone who studies mainly theory, I study atmospheric dynamics, atmospheric chemistry, and radiation. I mean, a lot of the physics that is applicable to, your solar system planet is applicable to exoplanets. And what I think really drew me to exoplanets in particular, and certainly illustrative about the system I'm talking about today, is the study of extremes. I mean, the same physics applies, but dial all of your, heating, your insulate, your chemistry up to 11. It's testing our understanding of how well do the physics that within our own solar system apply to these super, extreme end cases of what we think we know about how planets move, how planets migrate, how planets evolve. And so I think that kind of particular aspect really drew me to exoplanets in particular, is just like, if you can imagine a planet, it likely exists. I mean, that's, I think, something we can, feel more confident in saying now. And so it really sparks my imagination in terms of thinking about, not only what giant exoplanets might look like, but also habitable ones. If these giant exoplanets are so extreme and diverse, that really, I think, underscores the idea that habitable planets are likely to be that way too.
That's so true. And if you're trying to do some kind of atmospheric science, there are many worlds that you could look at, but this roasted planet is such an interesting case. You mentioned earlier that it has one of the most eccentric orbits that we've found on an exoplanet before, but how eccentric are we talking about here?
So HD 806's eccentricity is about 0.93. It orbits its star every 111 days. So, maybe only a third of the Earth's, whole year. But imagine that on a very extreme orbit where the majority of the time it spends away from its star. It's pretty quiet. It's pretty quiescent. But for the, roughly 1 or 2 days that it's very close to its host star, it's experiencing, all summer in a literal day. The temperatures rise to thousands of degrees Kelvin, where it looks more like maybe a Jupiter further away from the orbit, and then more like a hot Jupiter close into its orbit. And so what I find really exciting about this system is that all of that physics is taking place in this, 1 day sort of period. And it's just seeing how an atmosphere responds to such extreme insolation and how that affects the chemistry, the radiation, the atmospheric dynamics. And then additionally, what JWST can tell us about that period of time.
Well, it's going to be a really fun thing, but it also means that you have to be watching this world at a very specific time in order to get that JWST data, right? There's a very limited window in which it's very close to its star, right? So how difficult is it to actually get the observing time on JWST with such specificity?
I'm so glad you asked that question, because this has been a long, hard fought data set. And in fact, I think Lisa can speak on the other side of things, but I'll share this anecdote. So as it happens, the Cycle 1 selections included 2 programs to do a partial phase curve of HD 80606b. So it was my program, which is using the mid-infrared instrument aboard JWST, but then there was actually another program that was selected using the near-infrared spectrograph on JWST. And so I think, Lisa, you are on that program, right? Or you were?
Yes.
Yeah.
Yes,
yeah.
I was on that program.
Yeah. So James Secor is the PI of that program. I'm chuckling because looking back on it, it's one, everything works out in the end, right? But basically what was happening was, Cycle 1 got awarded like back in, what year was that, Lisa? It was like 2021 or something. It was, a few years before JWST actually launched.
2021.
Yeah. So when it came time to start scheduling them, they were more like 2023. And so for a while, it wasn't clear, like both teams were essentially getting like notifications like your observations are coming up. And so eventually we realized that what was happening was they had sort of scheduled us both, and then they were going to kind of execute one and not the other at that particular time. So it was like October of 2023. Is that right, Lisa? And so
exactly.
I remember because, we were the one that didn't get to go.
No.
And so I'm laughing about it now. No, it's fine. It's fine. It's just funny because they were sort of like, neither team knew that until we started sort of exchanging emails, because you can see all of these like long range plans in the Space Telescope system. So that program, the NearSpec program, executed in 2023. But as you alluded to, it's really hard to schedule because at HD 806, you really want to observe a very specific time frame. And so if you couple that with the observability of JWST to be, available to look at that specific time, it really, you've got roughly 3 windows a year, and then maybe one of those that is viable for JWST. And so we actually didn't get our data, the MIRI data, until last year. So it took, 3 or 4 years until we finally got our data. But in the end, I think, all's well that ends well. Like the data set is awesome. And we have the benefit now of using the NearSpec data in future studies. And, we're really interested in combining the data sets to see, two is always better than one, especially when it comes to JWST and the spectroscopic features that we have access to. And so, but that was at least from our perspective, how it all went down.
Yeah, I'm excited that you'll be combining both of the data set.
Yeah.
Hopefully the planet didn't change too much from year to year.
Yeah, I wonder too how much this world does change from year to year. I mean, going through such an eccentric orbit, getting so close to its star, right? There might be some wild changes going on. Who knows how much of it is blowing off, or even just the chemistry of this world probably changes wildly during that time.
Well, and you asked about the sort of orbital evolution of the system, and like while, largely speaking, it's stable, every system is dynamic in its own way. And so one goal of this program was to investigate, how much the orbit might or might not be evolving. And so one benefit of the system is that it's been, it was discovered back, I believe, in 2009. And so it has Spitzer observations. It has now JWST observations. It has TESS observations. It has ground-based observations. So there's a whole suite of eclipse and transit times of the system that we can compare against one another to say, oh, is it earlier or later than, that prior observation? And so what we're seeing is that, in fact, the orbit may be changing, maybe not significantly to suggest like another planet in the system or something like that, but it is tantalizing, let's say, evidence that, that's something that may be worth looking into more in future observations. So HD 80606 at its closest approach is about 0.03 AU, and then it's farthest approach, the Apastron as it's called, is closer to like zero point 0.8 to 1 AU. So 1 AU is Earth's distance from the sun, and so maybe that's a bit closer than that. But, you're talking about what, 10 times difference in orbital distance over that time, this 111-day orbit. So it's quite extreme over this whole period.
What actually happens to this world when it gets that close to the star? Like, what are you observing during that time?
You're observing a bunch of things all at once. And I like to call it, and I did in the press conference, it's JWST is like a one-stop shop when it comes to exoplanet physics, because the temperature is rising, but the temperature influences what chemically is in the atmosphere, be it, equilibrium species like, we expect maybe some carbon monoxide there, some water and other species. But not only that, there may be clouds or hazes in the atmosphere. One thing that's interesting is that we may be detecting a molecule that would suggest perhaps photochemistry is going on. The high insulation is sure to drive some more extreme chemistry. But that directly couples to, the molecules in your atmosphere dictate, how rapidly the atmosphere is cooling or heating up and cooling off. There's also dynamics that are moving the winds around, which Lisa will also talk about. All of that is happening all at once. And so I think the one thing, and maybe Lisa can speak to it on the near spec side, it's like you want a clean story, right? But the reality is all of this physics is happening all together. And so it's never going to be some like clear cut, like this is what we think is happening at this point. But at the same time, that's super exciting because understanding how all of these things interrelate is so fundamental to our understanding of planets in general. And so to see all of that play out in action is both frustrating, but also exciting. So that's, we're in the throes now of like finishing up our manuscript. And so trying to put a finer point on, maybe there's evidence for clouds or, the chemistry that we see at particular times of the orbit may not be suggestive of the chemicals themselves being available, but also being observable. And so if, say, for example, clouds are obscuring what we might be seeing, that's an interesting, hypothesis to explore.
Like Tiffany said, I think there's a lot of exciting thing, and especially for these planets, they're such complicated objects. So we used to think of these planets as just like a ball of gas with like some CO2 or methane, and then maybe we'd be able to see these transitions. But in reality, these eccentric planets are even more complicated because they also have seasons. And so just like depending on where they are on the orbit, they get different amounts of radiation. So there's a lot of different things to disentangle. But I think this is the most exciting about having JWST observations of them, is that it's like a huge enigma and a huge puzzle to kind of like look for it. And potentially maybe we'll get more observations in the future that will enlighten us in how we can piece together all of these different parts. But it's true that for now, it seems like the story is not super clear. But usually that means that there's more to discover about the planet.
I was reading that the timing on this planet's kind of peak brightness came in a little earlier than the weather models predicted. How can we possibly explain that? What's going on with that situation?
So one fundamental assumption we make when it comes to hot Jupiters, given their close-in distance, is that they're tidally locked. So essentially these planets have one side that's permanently facing the star and one side that's permanently facing away from the star. And when it comes to an eccentric hot Jupiter, we make sort of an additional assumption that it achieves the pseudo-synchronous rotation close to this periastron, the close approach to the star. And so essentially making that kind of assumption just very close to the orbit. But that's an assumption. And so one thing we've been wondering about is whether or not, so that the pseudo-synchronous assumption makes you assume a certain rotation rate that may not be correct. And so it's an assumption. With these observations, we can start to infer, perhaps maybe the planet is rotating faster than we think. Perhaps there's different chemistry that we're not expecting. I think in my talk, I was highlighting the idea that, maybe the transport between the day side and the night side, the winds between the day side and the night side are maybe less efficient than we think than the models predict, for example. But of course, it's likely to be a combination of all of those effects when it comes to interpreting the exact why.
If I may, Tiffany, can I ask you a
Please.
question? Because I'm really excited about these results
sure.
as well.
Yeah, absolutely.
So do you think that it's possible that it's not the planet that is rotating faster, but that the atmosphere is kind of like rotating faster than the planet is?
I suppose that's possible. So for previous data sets, so this planet was previously observed with Spitzer, the Spitzer Space Telescope. And so there were a suite of models that we're using to interpret this data set, but were also used to interpret that data set. But one fundamental assumption was they were varying the rotation rate. The assumption was made about the rotation rate, which was sure to change the day-night transport, the wind speeds, and so on. And so I think fundamentally, yes, that could be part of the answer that's sort of coupled with the rotation and the evolution of the system. So yeah, I think all of those sort of theories are still at play. And I think the whole cloud picture of it all is something that's maybe coming more into focus, in that we think maybe what we're seeing is up till periastron, up till this close approach, that it could be that the temperatures are so low that there are clouds that are present, but then when you approach periastron, this close approach, that the temperatures are rising so fast that all of those clouds go away. And that's why we see all of the stuff that we do in terms of the chemistry, for example. So there's a lot going on in this system, and still a lot to unpack, because all of this is like, theories we're working with. And so one thing I'll just say I'm really excited with the near-spec data is, the reason I say the power is together is that, with the near-spec data, you get an additional absorption band from methane or potentially carbon dioxide and monoxide. And so having multiple molecular bands for an observation just makes your detection that much more, well, hopefully, we'll see, more confident. And so that's one thing that we have, suggestions of things varying, for example. And I think similarly in James's paper, they maybe pointed to some of those suggestions. And so having the power combined, there's their Captain Planet reference in there. I feel like with our powers combined,
with our powers combined,
maybe there's an opportunity there to dig more deeply into the data sets together. So, so that's something I'm super, we're finishing up our first paper, but I'm already excited about the next one, to be able to sort of like dig deeper.
It's always so exciting to have more data on these worlds, because what I like to do is I try to imagine, using what we know about a world, like what would it be like to be there? And already this world sounds absolutely chaotic. Imagine that if you could, we have no evidence that anything could survive on this world, but if you could, that moment it gets closer to its star, that the clouds change, the temperature changes. What an interesting place to be.
Absolutely. There's a reason that it was selected as part of the Galaxy of Horrors poster series that NASA put together a few Halloweens ago. It is definitely not a place I would want to inhabit, that's for sure.
And speaking of that poster, I know you brought some to the press conference, and you thought that maybe they were all gone. I went back to that same room the next day and found some still there, and I hope you don't mind. I picked them up for the Planetary Society's trivia contest. So if anybody's listening to this and joins that contest, you might have a chance of winning one of these roasted planet posters.
Amazing. No, I'm thrilled that you took the rest of them and that they'll go to some worthy winners.
Lisa, you were talking about the winds on this world, and I think this connects very well to the topic that we were going to talk about next, which is this Corot 2b planet. Can you tell us a little bit, like, what is this world all about? And can you tell us a little bit about its star as well?
Yeah, absolutely. So Corot 2b is one of the first planets that were found by the Corot mission. So this was a French mission looking for, again, planets that were transiting. So basically looking for kind of like a dimming in brightness of the star as you monitor them. And so this planet was found via this mission back in like 2008, I believe. So it's a hot Jupiter on an orbit that is only 1.7 days. And so it means that the whole year on this planet is only 1.7 days. And because it's so close to its host star, it's called a hot Jupiter. And And there's one assumption that we make about these hot Jupiters on a very tight and circular orbit, which is that they're tidally locked. So basically, this means that the rotation of the planet, or the period of rotation of the planet, is the same as the amount of time that the planet takes to orbit around its star. So every time the planet moves forward in its orbit by a little bit, it will also spin on its axis by a little bit, such that the same side is always facing the star, and the same other side of the planet is always in obscurity. So it's never seeing the light of day. So in these configuration, we say that these planets have a permanent day side and a permanent night side. And so if you were to live on this planet, if you want to see the day, you have to travel to a different place. And if you wanted to see the night side or the nighttime, it's not a nighttime, you have to move to the night side. And there's this like sliver between these two hemispheres that's called the permanent dawn and dusk. So if you wanted to see a sunset, you would also travel to a specific place on the planet. And Kuro 2b was always kind of like a little bit of an oddball. So it orbits a star that is fairly young. So the star is also spinning very fast on itself. And this is how we usually date stars. And so the age estimate is a lot uncertain, but it's about 100 million years old. So this is young in terms of planetary, or at least in terms of a lot of the exoplanets that we know of. And the kind of like oddest thing about this planet is that it's super inflated. So it has a radius of 1.5 times that of Jupiter. And this is surprising because the planet is also massive. And typically for planets that are this massive, you would expect kind of like gravity to kind of like make them shrink into a smaller ball. So because it had this inflated radius, it means that there must be some kind of like mechanism or some kind of like heating in the interior of the planet that is making the planet puff up. And so this is really what started kind of like this investigation on Kuro 2b. So back in 2016, we used a Spitzer Space Telescope when it was still alive to essentially stare at the entire system, so the planet and the star, for a little bit more than 2 days. So basically, we watched the planet as it completed a whole kind of like journey around its star. And by doing this, because you're seeing the planet kind of like rotating on itself as well, you're seeing all the sides of the planet. So basically, all hemisphere of the planet. And you can't really disentangle, so you don't see the planet and the star on two different pixels. Normally, you get the brightness of both of them. But this is one way, by observing for a very long time, one way that we have to extract information about the planet without being able to isolate the planet on a different pixel. And essentially what we saw on this planet is that suddenly the peak, or the time where the planet was the brightest, was not when we expected the planet to be brightest. And so that sparked a whole kind of investigation as to why this planet was brighter after it's being eclipsed behind its host star rather than before.
That is a really weird one. I mean, what could possibly cause that?
So we had multiple hypotheses. So at the time, Spitzer had already observed multiple hot Jupiters to try to basically map their thermal emissions. So basically, by looking at different hemispheres of the planet, you kind of rebuild a map of how heat is distributed on the planet. And what we found with the Spitzer Space Telescope is that it had what we call the westward hotspot offset. So basically, the hottest spot, or the region, the hottest spot on the atmosphere of the planet is kind of like shifted west to the region on the planet that gets the most amount of starlight. And most of the other planets that we look at, or the other hot Jupiters that we looked at, either had no shift in their hotspot, or their hotspot was all moved to the east side of the planet. Kuro 2b had this like westward hotspot offset, and we had a couple of hypotheses for why this could be. We thought that perhaps the first one is that the planet is not yet tidally locked because the star is so young. It means that the planet is also young, and usually it takes some time for a planet to become tidally locked. The time scale itself we have some estimate for how long it should take. So we were expecting this planet to already be tidally locked, but maybe there's something that prevented it from being tidally locked yet. The other idea is that perhaps you have some kind of like weird patchy clouds that are blocking the kind of like brightness or heat or glow from the planet at different regions. And then the third hypothesis we had was maybe there's some kind of like deep magnetic field in the planet that is interacting with the atmosphere of the planet. So you can imagine that at almost 2000 Kelvin in temperature, the atmosphere starts to become ionized. So basically, molecules starts to break down into ions, and so the atmosphere is almost electric. And if there is kind of like electrons moving into a magnetic field, then both of them interact and kind of like disrupt the entire wind pattern that we would expect normally.
We'll be right back with the rest of my interview with Tiffany Kataria and Lisa Dang after this short break.
Hi, Bruce Betts here, Chief Scientist at the Planetary Society. Our organization is strongly committed to defending our planet from an asteroid or comet impact. Thanks to the support from our members, we've become a respected independent expert on the asteroid threat. So when you support us, you support planetary defense. It's a lot to do, and your support is critical to power all this work. That's why we're asking for your help as a planetary defender. Together, we're advancing the global endeavor to protect the Earth from asteroid impact. Imagine the ability to prevent a large-scale natural disaster. You can be part of this global effort. A gift of any amount to the Planetary Society helps keep this critical search going, protecting our planet and everyone on it. Visit planetary.org/Defend Earth to make your gift today. Thank you.
I mean, there's so many different things that could be going on in this circumstance. With a normal tidally locked hot Jupiter, what causes that offset in the hottest point? Is it the winds on these worlds, which I imagine are very strong because this is a world with a permanent day side and a permanent night side?
Exactly. So the winds are expected to be like up to a few kilometers per second in terms of how fast they are. For normal hot Jupiters without a strange magnetic field or strange like clouds, for example, we expect the atmosphere to kind of like be super rotating near the equator. Basically, they move slightly faster than the planet is near the equator, which cause what we call this eastward hotspot offset. So the fact that we observed the hotspot to be on the other side or on the opposite side meant that the planet must have been rotating significantly slower than expected.
I love you saying normal hot Jupiter because that's such an oxymoron, normal hot Jupiter. So it's the day-night insolation, this tidal locking, that induces waves that then transport a bunch of angular momentum to the equator. And so that's what fundamentally produces that super rotation. So
these are such weird worlds. I mean, it's really easy for me to wrap my brain around how a rocky world might work. But, you know, when you have a Jupiter like this, it's mostly gas and fluid. There's so much more complexity to the way that this could fall out. And is it possible that because the world is perhaps not tidally locked, that might be impacting the winds themselves? How does that work?
Yeah. So the rotation of the Earth itself also has an impact on the winds of our own climate and atmosphere. So essentially for these planets, how fast the planet would be rotating will directly impact how fast the winds will be moving. And if the planet is not totally tidally locked, it means that it no longer has a permanent day side and a permanent night side, like we used to think for these, again, normal hot Jupiters. And so there must be something else that's kind of like redistributing heat in a weird way, but for now, we don't fully understand this physics yet. So for most of the planets that we looked at, many of them are tidally locked. And so a lot of focus in the models that we create, for example, are focused on the like tidally locked planet. But for now, this is kind of like an exploratory stage where we don't really know what to expect on these non-tidally locked or the planets that are on their way to being tidally locked. So this is what's making this planet super exciting. With the Spitzer Space Telescope, we couldn't really disentangle between all of these scenarios that we had proposed for why the shift was happening. And so this is why with Aurora Caselli, who's a scientist at IDPAC and couldn't be here today because she just had a baby recently. He decided to find another kind of like method to confirm or maybe rule out some of the scenarios that we had proposed. So instead of using the Spitzer Space Telescope, which is a telescope in space, she basically convinced me that we could use telescope from the ground with a high resolution spectrograph to essentially look at these planets and determine what of these scenarios could be causing this weird hotspot offset that we see on Kourou 2b. From her work, we basically determined or found out that the rotation of the planet was slightly slower than we had expected. So this is kind of like a first evidence for a hot Jupiter that is not tidally locked. So it really makes Kourou 2b kind of like an oddball that stands out from all of the other hot Jupiters that we've looked at extensively with Spitzer, JWST, and other telescope on the ground.
Do we have enough observations of this world? And it sounds like we've been watching it for quite a long time. I know you've been working on this world for a long time, Lisa. Do we know that hotspot is stable in its location, or could it possibly be changing over time?
So we don't actually. We haven't looked at this planet quite enough, in my opinion. So essentially, this hotspot offset that we had detected was using observations that were taken back in 2016. And since there has been no hotspot offset measured for this planet again for the past decade. So hopefully in the next future cycles of JWST, maybe we'll be able to look at this planet again and really determine whether this hotspot is kind of like a steady state. So basically the hotspot is always, the winds are always blowing in the wrong way, or if there's something, or if these winds might be moving back and forth between blowing towards the east and the west. If that happens, then that might point towards maybe some weird magnetic field effects that we don't understand yet.
Mm-hmm. And you mentioned earlier, too, that this is a relatively young star that this thing is going around. And I wonder how the activity of the star and that point in the star's life is impacting this world as well.
Yeah, you're completely correct here. So I think this is what makes it Courage to be even more exciting, is that we're really seeing a planet that could potentially not be tidally locked yet and is just on its way to being tidally locked. And so we would be kind of catching a planet in this process of having its orbit circularize and its rotation synchronize with its orbit.
Can I ask, Lisa, since you were on the subject of the star, because I'm also interested in the system, as you know, how active is the star? Were you doing stellar activity sort of observations while the ground-based ones were taking place? Or what sort of activity do we think this star has, or have we observed it?
There's been some observations from the Kepler mission, but also from the TESS mission that allows us to basically see kind of modulation brightness of the star. What we see is that we know that the star itself has a couple of spots because it's young. So most young stars have kind of spots that are cooler or brighter. And as the stars spin on itself, you also see these changes in brightness. And that allows you to kind of measure how much contribution you get from the star versus how much contribution you get from the planet. Unfortunately, when the Spitzer observations were observed, we didn't have another telescope from the ground that were observing this the system at the same time. So if we were to redo this, I'd definitely have two different telescopes. One looking in the infrared, where we get the most information about the planet, and another one looking more in the optical, where we get the most information about the star, so that we can really make sure that we're disentangling the different signals here.
Are there plans to observe this world with JWST eventually?
This is our hope. Currently, there are no plans. We keep getting very, very close every time, but I feel like this smoking gun evidence from Aurora that the planet might not be tidally locked might be a lot of ammunition for observing this planet again.
It's got to be. I mean, I have to hope for that too. I would be putting my vote to that too.
Amazing. There's also one challenge. So the star is also very bright, which made it challenging to observe with JWST in the past. But it feels like every year, the engineers and scientists behind JWST keep on making the telescope even better. And so as of next cycle, I think we'll be able to observe planets that are even brighter than the limit of previous cycle.
It's amazing that they can make that instrument any better than it already is. I mean, come on, the amount of things it's teaching us.
It's awesome. Yeah, just to add more, when a telescope first launches, there's sort of a promise of certain modes that you give to the community. Like, we will have this mode, that mode. These are the things you can propose to. But over time, as you sort of get to know the telescope better, essentially, you can sort of say, hey, actually, this is not going to hurt the telescope in the long term, or something that we've tested and now feels ready for prime time. And so what Lisa's alluding to is these new modes that will hopefully get introduced in future cycles that is more amenable to bright objects like Corot too.
Looking at both of these planets side by side, one of them is kind of flash heated on this wild orbit, and the other one is being steadily cooked, but blowing its heat kind of the wrong way. What do you think that studying these extreme outliers ultimately can teach us about more, I hate to say it again, normal exoplanets, right? Maybe ones that might be rocky or potentially habitable?
So normally when you look at these oddballs, there's always another characteristic about the system that makes it weird. And so they're not just odd by mistake, they're kind of odd because there's a reason for it. And so the more you study the star and the planet, the more you find out what these weirdness about the planet is that could be tied to why the observations that we have of them are so strange right now. So for Korachubi, I think this inflated radius could be tied to why the winds are blowing the wrong way on this planet. And so we just need more observations to figure what that is.
Yeah, I'll add maybe a pessimistic take, but an opportunity in that, there's a lot of desire, obviously, to find and to characterize terrestrial exoplanets. But even amongst your run-of-the-mill Jupiter-sized exoplanet, even those exhibit such a large diversity of properties, of dynamics, of chemistry. And so if we can't, quote unquote, solve that problem, it's going to be very, it's just really illustrating the challenge that is the breadth of, once you move away from a hydrogen helium dominated atmosphere like you do for Jupiter or Saturn, like all bets are off. It's like there's so many different compositions that a habitable planet could have. There's so many different orbital scenarios. Is it in a single planet system? Is it in a multi-planet system? Is it orbiting a binary star system? Does it have a deep water ocean? Does it have a thick atmosphere? There's so many variables that when you start to think about life, habitable planets, astrobiology, all of those things where, the phase space is just orders tens and tens times larger than, the sort of narrow phase space, I would say, that is, the Jupiter, the Jovians. But that's the opportunity. And that's why I think, my soapbox always is why we need to continue studying these types of planets, the types of planets Lisa and I have been talking about, is that any test of our physics, any test of our understanding is going to pay dividends for extending that physics and that understanding to these broader phase spaces, to these, more diverse types of planets.
I think on temperate planets, or the planets that are more resemble ours a little bit more, there's so many different physics that are operating at the same time. But there's a quote that I read somewhere at some point, which says that sometimes looking at the most extreme planets is the most revealing in understanding a specific processes, or at least like disentangling the different processes that work at the same time on a planet.
Yeah, the more we learn, the more we realize that every world is kind of, even if they fall into these buckets, they're all their own special creatures, right? Just as there's diversity among humans, it's like there's a weird personality to each and every one of these worlds. And I think, the more we can study the extreme ones, it gives us a better idea of how everything else works, because it kind of breaks our hypotheses. It challenges us.
Absolutely. Totally agree.
I wanted to acknowledge, too, that Lisa, you work on hot Jupiters, but you're also known for your lava planet work. And I wanted to ask if you see any connection between the atmospheric dynamics on hot Jupiters and these other hotter but rockier worlds.
Yeah, thank you for asking this question. So it's true that lately I've been thinking about lava planets a lot more. In terms of techniques that we use to characterize hot Jupiters and lava planets, it's almost the same. And it's almost easier in some way to observe lava planets because they are orbit on even more extreme short orbits. Some of them take only like 5 hours to do a full journey around their star. The questions that we ask for these lava planets is slightly different. So we don't know how they fully form. We think that maybe they used to be larger planets and they used to have some kind of like gaseous envelope, but because of how close they got to their star, that atmosphere got blown away. So one of the big questions that we have for these planets now is there even an atmosphere to be found? And if so, is this atmosphere something that they've kind of like accreted during their formation, or is this something like a secondary atmosphere? So basically the atmosphere that they first had was blown off, and now what they have is basically gas that is being outgassed from the interior of the planet through volcanic activities or just like ocean evaporation. So quite a different kind of like planetary scientific question here, but in terms of what we do, how we observe them, how we tease out the different signal is very similar to looking at a hot Jupiter. But now we could only have done this with JWST back in the days. Spitzer was not necessarily designed to observe exoplanets. So the fact that it made a bunch of discovery in exoplanetary science truly was remarkable and is one of the legacy from this telescope.
Last question. If you guys could have unlimited telescope time on any exoplanet with JWST, what would you be looking for? Which planet would you go for?
Ooh, that's a good question. So I'm at heart, I'm an observer. And so kind of like my goal is to be able to look at a planet that is very similar to Earth. So kind of like looking at a rocky planet that is temperate. I think from now, there was a lot of promises that JWST would deliver kind of like first evidence of atmosphere and potentially biosignature on planets. But I think something that we're realizing after a few cycles and years of JWST is that it's going to take a lot of time and a lot of like telescope pointing time on that specific planet or on these planets to look at. So kind of like a special place in my heart are the TRAPPIST-1 planets, mainly because Spitzer has also made the discovery. Fun fact, I had an internship at IPAC about like 9 years ago now. And the first day I arrived, everybody was very busy and nobody wanted to talk to me because they had this like huge press release or press conference that they were getting ready for, but they couldn't tell me about it. And 2 days later, I found out that it was the discovery of the TRAPPIST-1 planets. So if I could dedicate like an unlimited amount of time to the TRAPPIST planets and kind of like study all 7 of them and see how the presence of an atmosphere on any of these planets is possible and how that relates to the activity of the star, I think there's a wealth of information and knowledge there.
Well, what about you, Tiffany? What would you do?
So I think I would go probably the other end. I mean, I think if given the time on JWST, I would sweep the floor of all the hot Jupiters that were observed with Spitzer that we haven't observed yet with JWST. I would do those because I think there's so much to be gained with the spectroscopic information, like with the phase curves that Lisa's been describing. Like Spitzer told us a lot, but it was only able to tell us so much because these were unable to provide the sort of molecular information that I think really enriches our understanding. And so I would include Corot 2b amongst those planets, of course, but even the, I don't know, observe in every geometry, for hours and hours so we can get phase curves of all of them. I'm a big fan of the 3D-ness of the planets and, how all of that ties together. And so any observation, I think, of the hot Jupiters that can enrich that picture. But additionally, the first paper I wrote as a grad student was about eccentric hot Jupiters. So like I will always have a soft spot for any eccentric planet, exoplanet. I think a good example is GJ436b, which is actually a Neptune-sized planet, but it is on a mildly eccentric orbit. I mean, mild in comparison to HG806. But that one, they've observed in transit and eclipse, but I think as yet haven't done like full phase or partial phase observations. And so that is one that I'm, it's a Neptune, but it's on an eccentric orbit. And so you can track like carbon chemistry over the course of the orbit, for example. And so I think that would be a really particularly exciting system to observe.
That really would be. Oh, man. But then we need more information about our own Neptune and our own system to really compare, right? So
yeah.
The real answer is we need 10 JWSTs and some, orbiters out to every single one of the worlds in our solar system to get this work done.
Absolutely. I'm on board.
Well, if we could snap our fingers and make it happen. But, I promise here at the Planetary Society, we'll keep advocating for this kind of work and maybe we'll get more instruments out there because there are so many mysteries, not just in our own solar system, but especially in the systems beyond. And we are so close to understanding so much more about these worlds. So I'm really excited to have you both on to talk about these hot Jupiters. It's been a long time since we had an occasion to talk about them on the show. So I really appreciate it.
Thank you.
Thank you.
One thing that came up in this conversation is this idea that the winds on these hot Jupiters can move faster than the planet itself is rotating. That's a phenomenon called atmospheric superrotation. The extreme temperature difference between the permanent day side and the permanent night side drives atmospheric waves that funnel momentum toward the equator. This accelerates the winds beyond the planet's own rotation speed. And that's part of why Corot 2b is so strange. Its hotspot is shifted the wrong way, so that suggests something is disturbing or even reversing that pattern. But superrotation isn't just an exoplanet thing. It happens right here in our own solar system. Here's our chief scientist, Dr. Bruce Betts, for What's Up. Hey, Bruce.
Hi, Sarah.
Hi. I am back from vacation. I came back from the mountain.
Whoa. Did you find inspiration on the mountain?
No, I got to take a lot of really beautiful night sky images. And strangely, I got a photo of the Andromeda Galaxy over the mountain I was visiting completely on accident. So that was awesome. But now I am returning back to work to fun hot Jupiter stories. It was only last month that I was at the American Astronomical Society meeting. So it's fun to finally get to talk about some of the cool stories that were released at that event. The winds on these hot Jupiters can move faster than the planet itself is rotating. But it's also something that we see in our own solar system. So I wanted to take a moment to acknowledge some of the worlds in our solar system that exhibit this super weird behavior.
Yes, Venus is the master of super rotations in the solar system. Venus is chugging along and rotating, and it rotates every 243 days. Its day relative to the sun is actually much shorter than that, but still long. But it's 243 days this thing takes to very slowly rotate, and yet the cloud top winds and the equatorial region are booking around the planet in 4 days, 4 Earth days, compared to a 243-day rotation. And it's driven mainly by thermal tides, basically uneven solar heating. But it's weird. And you can actually see it. The effect of it, at least that's my understanding, in the pictures of Venus that are UV. The visible pictures are usually very, very bland, which is why people don't show them very often. And so you'll see this ultraviolet pictures that show the winds, and you'll notice in the equatorial region, there's a bulge off to one side in the winds. It's all kind of sweeping around, but it's crazy. And it's interesting, and it's been an idea for balloon missions there, and then used somewhat by the Vega balloon missions, that you can really cruise around rapidly in these super rotating winds.
That's really weird. Like I would expect that kind of behavior from a gas giant or something that can do that kind of differential rotation, get all sped up around the center. But with a rocky world like Venus, I mean, it makes sense. It's doing the same thing where it's really hot on one side and not so hot on the other, but still.
You don't often see this kind of behavior in a terrestrial planet. All the planets are pretty weird. That's part of why they're so interesting, because they're so weird and so different. Jupiter and Saturn have equatorial jets, so kind of more localized things. They also get crazy and move faster than the overall rotation. But now we've got Jupiter, the fastest rotating planet in the solar system, at about 10 hours for its day. Of course, if you watch a time lapse, you got all sorts of wind activity going on there, and things going one way and things going the other. It's crazy. And Saturn does very similar things, but doesn't have the color variety, so it's a little tougher to see. These go down thousands of kilometers deep, according to Juno and Cassini observations. So they're also different. One, that you can go thousands of kilometers in an atmosphere. You're on a giant planet when that happens. And anyway, yeah, weird stuff. And so finding that outside the solar system is not entirely surprising, but pretty nifty that they can measure such a thing.
And it's really cool. The results coming out of JWST looking at these worlds and not only seeing things like that we can interpret as wind speed, but also as cloud formation. And this is only the beginning of us being able to explore these exoplanets.
This is only the beginning.
Only the beginning.
And it's, I mean, I don't know, you mentioned it on the show, but they're really far away. I mean, really far away. And they have this big bright star usually nearby, so it's really hard to do stuff. But when we keep getting cleverer and cleverer, and you get things like JWST and future telescopes will do even crazier things trying to check these things out.
Another thing I did at the American Astronomical Society meeting was go to a gathering of the people from the Habitable Worlds Observatory. So I'm hoping to have them on sometime soon to talk a little bit more about how we can learn about these smaller, more Earth-like worlds. But that's even further in the future.
Yep, that's the big space telescope of the future, we hope. And will be designed to do crazy stuff like this. Exoplanets, of course, are just quite the burgeoning field. When I was in school, there were no exoplanets. Well, there were. Well, I mean, if an exoplanet falls in the forest. But now we've got over 6,000 confirmed, I believe, as well as a few thousand more possibilities, and we're going to get even more from all sorts of stuff. Hey, why don't we go on to Random Space Fact Rewind? we're going to talk about the fact that we just passed the 50th anniversary of the Viking 1 landing on Mars that occurred July 20th, 1976. And your random space fact is it was originally scheduled to land on July 4th, 1976, the bicentennial for the United States, 200th anniversary of that whole Declaration of Independence thing. But then when they got there, pictures and data showed a planned landing area looked too rough and rocky. So they tried to find another one and figure out how to get there. And then they were able to land. It's like, hey, let's pick another anniversary. How about the 7th anniversary of Apollo 11 on the moon? And so they landed on July 20th. That's how it goes. And there were still a bunch of rocks. We've gotten more extensive data, including from the Viking orbiters, and then after that to do a better job of predicting what might be on the surface. But hey, Viking Lander 1 and 2 both worked. A little bit of luck of not landing on one of those rocks. But yeah, so there you go.
Can you imagine being one of those people that are like, we got to hit the deadline. It's the 200th anniversary. And then, well, I guess we'll go for the moon landing anniversary instead.
Yeah.
I bet that was a very stressful week for those people.
Yeah, I mean, I'm kind of impressed they turned it around that quickly after boarding the first landing site. But more important to have your spacecraft work than meet your anniversary deadline, or at least that was the theory. And Viking Lander 1 showed us Mars from the surface.
So cool.
Super cool. I mean, now we just rove around and we're just super cool and check things out. But that was, that was new. It turns out Mars is pretty red.
Now, isn't that weird how just a few decades ago, there was all this stuff that we didn't know. And now I can nonchalantly just look up pictures from what Perseverance was staring at yesterday on Mars. Like one of these days, people are going to be able to just look up direct images of other worlds. And they're probably going to be completely nonplussed by it.
Now, you can look them up now. They still put the raw data from a lot of those missions, just pump it onto the web right away. Not all of them, but a lot of them. So if you're into it, you can get it fast, furious, and all the thousands and thousands of images coming down. Speaking of images, or maybe not, everybody go out there, look up the night sky, and think about accidentally seeing and imaging the Milky Way. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who share our fascination with worlds beyond our own, whether they're in our solar system or orbiting distant stars. You can join us and help keep the exploration of extreme worlds like these going at planetary.org/join. Mark Hilverda and Ray Paletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah El Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.